Hi children, now you are familiar with the term gravitational field intensity and acceleration due to gravity. In this current session, I am going to discuss about one more new term, that is potential energy. So, we will see what is potential energy, what is the potential and how field and potential can be related in gravity. These things all we will discuss and then do some questions also to clarify our concept. Let's get started. In last session, we had discussed about variation in acceleration due to gravity in detail. Again, I am going to discuss about gravitational field intensity, but this time it is not due to Earth, it is due to different kinds of shapes, because as we know, all the forces exert gravitational pull on other bodies. So what will be the field intensity due to different kinds of shapes? First, let us consider gravitational field due to a point mass. We know this very well. For point mass, the result can be written as, now I am writing field intensity by E, so this can be written as minus gm/r square, where r is distance from the point mass. If we have to calculate field intensity at a point P, which is at distance r from mass m, then its field intensity can be written as minus gm/r square. And what about the direction? Direction has to be along unit vector r, which is away from the mass m. The next is a shell. Shell is a hollow sphere. Now for shell, two cases we have to remember. The first, when point P is outside the shell. First we are considering P being outside. So if P is outside, then the shell behaves as it is a point mass, and this is not only for gravitational field. This will be the same even for electrostatic field as well, because both the forces are inverse square law of force. So for a shell, this is actually property of shell, that for the points outside the shell behaves as it is a point mass which is situated at its center, and then we can write field at P to be equal to, its value will be minus gm/r square, as the case with a point mass. Its direction has to be along minus of r. So this is away from the shell. Another case we have to consider when P is inside. So if P is inside, then intensity at P has to be equal to 0. So this is the behavior of shell. Now consider case of a solid sphere. Again, solid sphere can be assumed as made up of a number of spherical shells. So if we consider solid sphere, we have to consider both the points when P is outside, and for outside, as you know, the sphere behaves as it is a point mass which is situated at its center. So EP again can be written as minus gm/r square, and direction minus of unit vector along r. What about the inside? This time it won't be 0. So for inside points, field will be equal to, we had used this result while calculating acceleration due to gravity inside the earth, because earth is also a solid sphere. So already we had derived this as for the earth. The same result I am going to use here again. It will be given by minus gm r upon r cube, and direction given by minus of ur. So this is the result of gravitational field intensity at a point P which is inside the solid sphere. What about the ring? One more shape I am going to consider is due to a ring. This is also very helpful because generally we get question from these shapes. So if I write field due to this ring which is at a distance of x from the center of ring, and radius of ring is r, mass of ring being equal to m, field will be minus g mx upon r square plus x square, this whole to the power 3 by 2. Its direction has to be towards the center of ring. So if I am going to consider this direction as x-axis, it has to be towards minus of I. So these are gravitational field due to different shapes. Now let us talk about potential energy, and since we are dealing with the chapter gravitation, so here it has to be gravitational potential energy. As you know, what is potential energy? Potential energy is defined as negative of work done due to internal conservative force. So here also potential energy can be defined as negative of work done due to the gravitational force, which all you know that it is a conservative force. So now I am going to define mathematically gravitational potential energy. Let us consider a particle mass here, that is A. It has some mass m1, and another particle mass here which has some mass m2. They are initially at separation r1, and finally this B is dragged here to separation from A as r2. We are interested in calculating the change in potential energy. So we are interested in calculating this delta U term. What it should be? It should be minus of work done by the gravitational force. So it can be written as minus of F_dr. Now since here the force is not a constant, its value is varying with separation. So we have to consider one intermediate position where this distance is equal to r, and then it has to be displaced by a small displacement, that is dr. What will be the work done for this small displacement? It can be integrated over from r1 to r2 to get the whole work done. So now if I substitute the values, this will be equal to g m1 m2 upon r square dr. Minus sign has become positive now because f and dr are in different directions. So one minus sign will come here from the dot product, and then this becomes positive. Now let us write what after integration it will be. Limit has to be of course from r1 to r2. On integrating, this will be g m1 m2. Then it has to be 1 by r1 minus 1 by r2. So this is the result of change in potential energy, and change in potential energy always should be written as final energy minus the initial energy. Now what if we consider initial potential energy to be 0? So this term will be 0, and we assume that at infinity the potential energy is 0. So if we take infinity as a reference, then R1 can be put as infinity, and we will get finally UF to be equal to minus G m1 m2 upon R. This is how potential energy is defined for a system which is consisting of two particles m1 and m2. We can extend this concept to 3 or even more particles. In this case, we have to simply sum up all the potential energies for all the pairs, because as we know potential energy is a scalar term. So to get potential energy of the whole system, only we have to write potential energy of all the pairs. And if there are n number of particles, then number of pairs should be equal to, it will be n multiplied with n minus 1 by 2. This is the number of pairs when total number of particles are n. And in that case, we have to write U total to be, it will be U12 plus U13 plus U23 plus U31. In this manner, we can add all the potential energies for every single pair. Now let us do one question based on this concept. 4 particles each of mass m are placed at the vertices of a square of side A. What is the gravitational potential energy of the system? Let us consider these 4 masses which are at the vertices of the square. So these are the 4 particle masses, each of them being at separation A. We have to calculate potential energy of the whole system. Just now I had said that potential energy for whole system has to be equal to sum of potential energy of all the pairs. So how many pairs are here? It has to be one pair for these two masses, then for these one more pair, one more pair. These are the four pairs, and then two more pairs are there for the two masses which are along the diagonals. So we have to write here for 6 pair of masses total potential energy term. For 4 of the pairs it will be having the same value because they are at same separation, and we can write value to be equal to 𝐺𝑚² A. And for other two pairs which are along the diagonal, we have to write -2 𝐺𝑚². Now the distance has become √2a. So on solving this, we will get -𝐺𝑚²/a can be taken as common. It will be 4 plus √2. This is potential energy of the whole system which is shown here. One more question I have. Distance between the centers of two stars is 10a. The masses of these stars are m and 16m and their radii a and 2a respectively. Let us first draw the spheres. One is having radius 2a, other is having radius a, and distance between these two are given as 10a. The masses are 16m for the bigger one and m for the smaller one. A body of mass m is fired straight from the surface of larger star towards the smaller star. What should be its minimum initial speed to reach the surface of the smaller star? We have to obtain this expression in terms of g, m and a. Okay, let us consider one particle which is being fired from the surface of the bigger star. As it has simply to reach the smaller star, so we can assume that on reaching the smaller star, its velocity has become 0 because we have to calculate the minimum initial speed required. For that, we have to consider that on reaching the smaller star, the velocity of particle has become 0. Let us now write the energy conservation. When the body or the particle is at the surface of bigger star, now we have to calculate the minimum speed at the surface of bigger star. So the speed should be just sufficient to take it to a point where gravitational forces due to 16m and m balance each other and net force becomes 0. Let us consider that point to be here, which is at a distance x from the center of the bigger star, because when the particle reaches here, due to the field of smaller star, now it will move towards the smaller star. So we have to simply send the particle from the surface of bigger star to this particular point, which I have written here as P. Let us now write, because at point P, gravitational forces due to both the stars has to be same. So we can write 16 gmm upon x square to be equal to gmm upon 10a minus x square. On solving, we will get these all terms will get cancelled. We can take square root and then 4 by x can be written as 1 by 10a minus x. On solving, we will get x to be equal to 8a. So if the particle reaches at a distance 8a from the center of larger sphere, it will be able to reach the surface of smaller sphere. Now let us write energy conservation. That will lead -16 gmm upon 2a, which is the potential energy when the body was at the surface of 16m, plus its kinetic energy, which is half mv square, minus gmm by 8a to be equal to -16 gmm by 8a minus gmm by 2a. And on solving, we will get v square to be equal to 45 by 4 gm/a. So we got finally v to be equal to 3/2 root under 5 gm/a. This is the minimum speed required for the body if it is projected from the surface of bigger star so as to reach the surface of the smaller star. Let us move to the next concept in potential energy, that is gravitational potential energy in the field of Earth. Now we will see how potential energy varies in the field of Earth. Let us consider that a particle is at some height which is a1 from the surface of Earth, then it goes to some other height b which is at a distance h2 from the surface of Earth. Of course, radius of Earth I can take as r, this O being the center of Earth. Now if we have to find expression for gravitational potential energy, then we have to write work done in lifting this a point mass from A to B, and that will be work done from A to B. If I write, it will be equal to force multiplied with the displacement. So this is force into displacement. Both the points are in the gravity field, so it can be written as mg h2 minus h1, and h2 minus h1 is actually the change in these two heights, that can be written as delta h. So this work done will be equal to mg delta h. Generally, we write this mgh itself as potential energy of a body if it is taken by a height h in the field of gravity. Now let us do one example based on it. If g is the acceleration due to gravity on the surface of Earth, find the gain in potential energy of an object of mass m raised from the surface of Earth to height equal to the radius r of the Earth. Here, this height is not a small height, it is equal to the radius of Earth. So directly we cannot apply the result mgh. That is valid only if g is constant, because while deriving we had taken g outside the bracket and then written simply h2 minus h1 as delta h, which is true only if h is a small height. But here the height is very large, so we have to proceed in a general way. Let us write acceleration due to gravity. So on the surface of Earth, it can be written as gm/r square. And so we can write gm to be equal to small g multiplied with r square. From here we can write potential energy initial, which is at the surface of Earth, to be equal to, this is minus gmm upon r. Now when it has reached to a height equal to radius of Earth, then final potential energy can be written as, this time the distance has become from the center of Earth as 2r. So it will be minus gmm/2r. And so we can write change in potential energy, which is uf minus u initial, to be equal to minus gmm/2r. Then minus minus becomes plus, it is gmm upon r. On solving this, the result will be gmm upon 2r. As you can see, if we had applied directly the formula mgh, the result would have been gmm/r, which is not correct, because this time the height is not a small height, so directly we cannot use the formula mg delta h. We have to proceed in general way and then get the result, that is equal to gmm/2r. Now we have to see what is gravitational potential. Already we have calculated the potential energy. So gravitational potential directly it can be defined as, generally it is denoted by V, which can be defined as potential energy per unit mass. So if I substitute for a particle mass the value of g, that will be equal to minus g mm/r, and then this m, these two got cancelled, the value will be equal to gm/r. So if we say that gravitational potential energy is the work done in bringing a mass from infinity to the point concerned, to define potential we can say that it is again the work done in bringing, but this time for a unit mass from infinity to the point concerned. And this is the formula we will get for a particle mass, which is equal to minus gm/r. Now let us see what is relation between gravitational field and potential. As we define potential energy, that this is equal to minus of integration of f dot dr. So this u can be written as mass multiplied with v, that is equal to minus, now f can be written as m into g dot dr, and these two m got cancelled. We get the final result v to be equal to minus integration of g dot dr. This is relation between potential and the field. Now to solve the question, we have to write v to be equal to minus g dr can be written as dxi plus dyj plus dzk. And what if potential is given and we have to calculate g? Then we can write value of g to be equal to minus del v by del r, which is known as partial differentiation of potential with respect to r. And since g is a vector term, so we have to write g to be equal to, this will be del v by del x I, minus sign has to be there, minus del v by del y j, and minus del v by del z k. So depending on whether potential is given or field is given, we can calculate the value of other. Let us see one example. A particle of mass 1 kg is released from rest at a point where gravitational potential is 5 joule per kg. After some time, it passes through a point B with a speed of 1 meter per second. What is the gravitational potential at B? Let us see how this can be calculated. See, as the particle is moving from A to B, its kinetic energy, as you can see, is increasing because it was initially at rest and now has gained a speed of 1 meter per second. So its potential energy of course must decrease, because only then mechanical energy will remain conserved. So we can write from conservation of mechanical energy, kinetic energy at A plus potential energy at A to be equal to kinetic energy at B plus potential energy at B. And on substituting the values, it will be half mv square plus ub, and we got ua minus ub to be equal to 0.5. Now since it is asking for potential, so we have to divide the term with mass, and then ua minus ub upon m will be equal to 0.5 upon 1 joule per kg. From here we can write Vb to be equal to, it should be Va minus 0.5, and as Va is given 5 joule per kg, so this is 5 minus 0.5, which is equal to 4.5 joule per kg. This is the potential of point B. One more example I have. The gravitational field due to a mass distribution is given by k by x square I, where k is a constant. Assuming the potential to be 0 at infinity, find the potential at a point where x is equal to a. We know the relation between potential and field, so directly it can be written dv as minus I dot dr, where I have written for field intensity, so this is minus I dot dr. From here we can write dv is equal to minus k by x square, dr can be written as dx, as field distribution is only along x direction. And then on integrating, dv will be equal to minus k taken outside, this is integration of dx upon x square. The limit should be, because potential is 0 when x is infinity. So initial limit has to be infinity for x, and final it has to be a, for which we have to calculate the value of v. So on integrating, we will get v to be equal to k by x within limits infinity to a, that will be equal to k upon a, which is our desired result. With this, now our discussion of potential is complete. We defined potential energy, potential, and then related the two terms potential and intensity. And we solved some questions as well. So let us now wait for the next session, where we are going to discuss motion of different planets. But before that, where we are going to discuss the 3 Kepler's law. Till then, keep very good care of yourself. Bye.